Problem 4. Are you ready? Are you ready to rock, Squidward? Okay, problem 4. We're getting down there. We're getting down there. Yes, we are. Okay, the rate constant. Okay, this problem, I'm reading it off for you. Okay, you're reading at home. The rate constant for a second order reaction, and it gives me the reaction. Okay, it's got the 2 nitrogen dioxides making 2 nitrogen monoxides and molecular oxygen. All right, is. So they tell me the rate constant here. I have the K value. I have the K. It's where is it? 0.54. So I'm going to write that down. 0.54. K is 0.54. Weird units. Again, the units are always different. Don't worry about it. Just use the number at 300 degrees. Okay. How long in seconds? Sounds very similar to the last problem. But the last problem was a first order reaction. This is a second order reaction. Okay, keep that in mind. How long in seconds would it take for the concentration of the nitrogen dioxide to decrease from 0.62 molar to 0.28 molar? Sounds very similar to the last problem. It wants me to find a time. You start out with a concentration. You end up with this concentration. How long would it take for that time period to go from this concentration to this concentration? Yeah, it is. It's got two differences. One, it's a second order reaction rate, second order reaction. And two, they didn't give me percents. Nice, I can just put the numbers. They give me actual M values. Oh, we forgot about Billy. Billy, in the last problem, did you figure out using the 2 and the 0.01? What did you? I got 150. So did we, Billy. See? Okay, comes out to be the same. So those percents, okay, we're not giving percents. We're actually giving values here. And we're going, yeah, nice, sweet. We don't have to be angsty Billy won't get all angsty. Okay, so what do I do in this problem? This will be a relatively quick video here because I have an equation for this. That's that other equation I was showing you in the last video. It's this equation right here. That is the second order reaction rate equation. So maybe write that in here, second order. Okay, that's what we're going to use. It's a little different. It is actually another step of calculation derivation to get to this one. You don't need to know how to do that, just need to know how to use the reaction. So let's go ahead and take a look at this reaction equation. And it's 1 over concentration equals KT, no negative this time, no negative, plus 1 over concentration times 0. So it's similar yet different. This part's similar, but we got rid of the negative. This part is similar. Here's A at the start. Remember, concentrate at the start. The 0 means start. And this is the concentration at the time that you're looking at. Okay, so that's that. And we got rid of the LNs. The LNs are gone. So now it just becomes a fraction. This is actually easier algebra. It really is. It's easier algebra. Let's dive in. Let's get this done. Let's see. This could be pretty quick here. How long in seconds would it take for the concentration to go from 0.62 to 0.28? So we have that one reactant, the nitrogen dioxide here. It's going to break down. It's a second order reaction. Okay, let's just kind of review that. Second order reaction, there's one reactant, which means its exponent must be a 2 if it's a second order. So if we double the concentration, we double, okay, just to review that. We don't need to know that in this equation. That was just a little review. Okay. So 1 over this is the concentration at the time we're looking at. So just be careful you don't put these in the wrong spot. This is the concentration at the start. At the start it was 0.62, and we're trying to find out how long it takes to get to 0.28. Where does the 0.28 go? Here. 0.62 goes here. That's at the start. The higher concentration is going to be the one at the start, right? I mean, that's the highest concentration, then it breaks down. Hopefully it makes sense to you. All right, so this would be 0.28. I keep forgetting these numbers. Brain's not working good today. 0.28 equals K. And we were given that right here, 0.54, times T, or you might want to call it X, plus 1 over the concentration at the beginning, which is 0.62. There it is. Do the algebra. This is just a fraction. So I'm going to take 1 and divide it by 0.28. Take 1 divided by 0.28. All right, 1 divide 0.28. 3.57. So 3.57 equals 0.54 times x plus 1 divided by 0.62. So So 1 divided by 0.62 is 1.61 plus 1.61. All right, there it is. Subtract, get the x by itself, subtract 1.61 from both sides. So this goes away. Subtract 1.61 from this side, minus 1.61. That's going to be 6. That's 15. Minus 6 is 9. 1.96. Let's just verify that. 7, 15, carry the 1. 1.96. All right, so I'm running out of room down there. 1.96 equals 0.54x. Divide by 0.54. X is going to be not very long. This is going to be a quick time. 1.96 divided by 0.54. This is like quick time. 3.63 seconds. 3.63 seconds. So to use from 0.62 molar to 0.28 molar, yep, we've gone down. We've used about half of the concentration, and it didn't take very long for that to happen. 3.63. So it was pretty quick, and we went to just below half. We can actually figure out the half-life if we wanted to. We can go back and use that half-life equation. It's not asking us to do that, but T1/2 equals 0.693 over K. Now that we have the K, we can figure out what the half-life is. But I'm going to do that anyways, just because, let's just see, it should come out to be not too far off of this. 0.693. It's not going to be exact, and these half-lives are actually, they're not linear. They're actually, they do this kind of exponential thing. I forgot what I was doing. Oh, I'm dividing by half-life, or the K value, 0.54. 1.28 seconds for half of it to go away. So yeah, it's pretty quick. The half-life is pretty quick, and we determined that. Yeah, this didn't take very long. Where is it? Here. This didn't take very long. Seconds. So we've lost more than half. We've lost more than half. From 0.62 to 0.28, we've lost more than half of it, and it took more than half-life. So, all right, it's just chemistry, numbers make sense, right? Hopefully, that was it for that problem. That was just using the second-order reaction equation, and if you have a second-order reaction, you want to figure out time, which you will. Then make sure you're using the correct equation. All right, that was a nice, quick video.